Now to the meat of the matter. How many people here have a scope? Okay, of the people who have raised their hands, how many people use it routinely? Okay. How many of you have it collecting dust in your toolbox? Okay. That's really good, because typically when I ask that question, I get maybe 1 or 2 hands from the entire room. Of all the shops that I worked at in Florida, I was the only guy that ever had a scope or ever used a scope. I actually had a fellow not too long ago tell me that a scope is an antiquated piece of diagnostic equipment that has no value in modern diagnostics. Go right ahead with that. The whole purpose of the whole goal of this presentation, and I call it a presentation because I'm not any better than anybody else in this room. I'll share with you, but I'm not going to pretend to teach you much. I think we'll learn from each other. The whole goal is that if you're not using a scope routinely, I'm going to show you some ways that maybe you can use it that you haven't thought about. That will speed up your diagnostic efforts, maybe make you a little more money, make life a little easier for you. And if you're on the fence about adding one to your arsenal, maybe this will push you off the fence and on the plus side, and you'll see the value in it. 2 things I'll tell you right at the bat. Scan tools have become very powerful, no doubt. But they only tell you what the module wants you to know. They're not always telling you the truth. But if I connect a scope to a sensor or a circuit or anything else for that matter, I'm going to get the truth. I'm going to get the reality of the situation. Another thing I like about a scope is that a scope gives me a graphical representation of wherever I'm looking at. It gives me a picture that I can sit back and look at, maybe over a cup of coffee. And that was one of my favorite games when I was a kid. What's wrong with this picture? And then that what troubleshooting is, the more you know about the system that you're working on, the problem that you're trying to deal with, what the picture's supposed to look like, the easier it is to look at the picture and find out what's not right. Anyone start off with an old analog scope? Yeah. When I first started learning about testing techniques with a scope, it was back when early days of IETN. And there was 1 or 2 people on there that were playing with their flukes and doing more than just secondary ignition patterns. And some shops, maybe you remember the old Firestone, Mastermind, Master Tech boxes? They had it on an I-beam. You rolled that thing across a couple of bays and hooked every 50 cables up to the car, and it just ran this pre-programmed test for you. Well, that had an analog scope on it. Now, the first time that I started reading about some of these like fuel pressure, current ramping, or cam crank sensor tests, and guys were looking at me like, what the hell are you doing? And if you wanted to know what was right, you either had to figure it out on your own or start saving the good stuff that you found. Now, you've got all kinds of choices, right? This one here is sitting in the back in the UEI version. I had the same one, the ADL 7100. That was my very first personal scope. You don't think much about it, but it was kind of a cross between an analog scope and a digital scope in the sense that it has a digital storage scope, which I'll cover in just a second. But once the pattern was there, it was gone. Just like the analog scope. You couldn't save what you saw in the analog scope, right? The old Sun machines and those. Before we go much further, and I hope the volume will be loud enough, I want to share the latest in Pico technology with you. You have to kind of listen real close.
Pico Technology's latest concept to complement our range of USB oscilloscopes, a lighter, more portable display than a laptop etchoscope. Features include single channel stream recording to a screen of 1800.
Can you see that sine wave?
Maybe a few bugs to iron out before release though.
But what is a digital source? It's a oscilloscope. It's like this. When you start looking at sampling rates, what you're asking the scope to do is it doesn't draw a real-time trace. It collects data just like a digital multimeter does. And it plots those points on the graph. It connects the dots. Now, the more dots you have, the more accurate the representation you have on your screen. And in modern scopes, we've come light years from where we started off. If you remember the old fluke captures, especially on the vertical, how they look like a step going up, that was simply a matter of vertical resolution and sampling rates. Some of the modern scopes, this is just an example from a pattern that we'll look at in a little bit. Look at what this is sampling. It's taking a sample every 3 microseconds. And all the little dots that's connecting on the screen, well, on this capture, there's almost 2 million of them. How accurate do you think that trace is going to be? Now, how many of you guys that own scopes, how many of you own a PC-based scope, a computer-based scope? Okay. And the rest are handhelds, Modus, okay, or the Vantage Pro, both excellent handheld units. But most of these newer scopes will allow you to capture a big portion on one screen and then zoom in on what you caught. So the more points that I can plot, the more I can zoom in and still maintain some accuracy in what the pattern's going to be. I think scope testing saves me a lot of time, and I can use it on nearly every system on the car and then some. Anything that you can measure with your multimeter, you can measure with your scope. And there's a lot of things you can measure with your scope that you can't touch with your multimeter. Okay. I would say this to you. The only limits to your scope are your own personal imaginations. Think of all the tests that we now know of that people are using their scopes for. Remember when fuel pump current testing first came out, or you first started reading about it? Ooh, I got to try that. Now that's relatively commonplace. And cylinder pressure testing, how many of you guys are doing that? Okay, that's a fairly new one. But all of these didn't just pop up out of nowhere. Somewhere there was a tech like you who had a scope out, who had a problem in his bay, said, I wonder what would happen if. And he took a test. It worked for him. He shared it with his buddies. And then his buddies shared it with their buddies. Then I hear about it and I'm going like, okay, I have 120,000 shops that I reach every month. That's almost 500,000 techs. I think I'll try to spread the word. Okay? That's my job. Are you finding more problems with intermittent sealing in the engine, causing misfires or drivability issues, especially on GDI cars? I've seen some GDI cars 15, 20,000 miles on them and not sealing because of the buildup. How easy is that to find when an engine seals one minute and doesn't seal the next? Maybe I'll show you a few ways that you can catch that. We're going to start with something that I thought, first of all, made life a lot easier for me. And is everybody getting around okay with my voice? You can hear me in the back okay? Okay. Is mechanical testing of the engine health before we even start? We're going to focus on this on the May 31st webcast. We're actually going to do a lot of these tests on a live car so that you can see the hookups and the traces as we're actually doing the work. And it came about this several years ago when a Chrysler minivan, I think it was a 3.8, the ones that had the problems with the exhaust valves. A little might misfire at idle. All the rest of the time it was fine. But at idle it was just this nagging little skip. Okay. And I found it using the method I'm going to share with you here. And now because I got bit by that, I make this part of every test or every drivability diagnostics that I do. It's simply doing a relative compression test using the amount of current drawn by the starter. How many of you guys have used this test? Okay. Any modern scope will detect as little as 10% loss of compression in a cylinder using this method. It's very simple to do. All you have to do is throw your high amp clamp around the battery cable, disable the fuel, and crank the engine over. Okay. When you're looking at a pattern of any kind, one thing I would encourage is don't focus on the trees. Look at the forest. Look at literally the big picture. And look for what stands out as being out of place. When I first started using scopes, I didn't hear about a new testing technique. Every time I learned a new method, I would see it in every pattern I took, because I would make it be there. Okay? Don't fall into that same trap. Don't try to memorize a certain pattern. Think about what's going on when you're looking at the pattern. What's going on here? I got the key turned on. I hit start. As soon as I hit start, the solenoid closes, starter motor starts spinning. It takes a little bit to get that mass moving, but then finally it settles down and it starts cranking at a steady RPM. Now, what affects the current draw in any motor? The pressure, the work it has to do. And that can be a starter motor, it could be a fuel pump, it could be a window motor. The harder it is for that pump to do the work, the more current it's going to take, right? And now at this time base, every little time that the piston is trying to work its way through compression and the motor is fighting that battle, it's going to take more current. So that's what you're seeing in each peak. So every peak represents what then? Compression. Top dead center compression, right? Is there any condition where I can have a pattern that looks just like this one, looks uniform, but still have an issue? What if there was a factor that made the compression low on all cylinders? The camming time was off. Okay? So one of the things I would first encourage you to look at is what is the peak-to-peak current? This one's almost 54 amps. That's pretty strong. If I didn't see that high a peak, if they were all nice and uniform but a lot closer in height, shorter if you will, then I would have a question about the actual total compression of the cylinders. You see what I'm saying? Relatively to each other, they're fine. It doesn't mean that they're all at 100% of what they should be. How about cranking speed? Now, as a side note, before I get too deeply, the handouts that we have for you, I mean, you guys get those handouts, and they're just like pictures of the PowerPoint, and that's it, you know? And you have it in your toolbox, and you go back to it 3 months later, and you try to remember what went with what picture. Well, I want you to make little notes in these that I gave you so that you can throw that in your toolbox, and a month from now, 6 months from now, you can go back to that and apply it to whatever you might have sitting in your bay. Do I really need to measure cranking RPM? I mean, I haven't been doing this for a while. I can tell if the engine's spinning over slow or fast or skipping or whatever. But what if I want to document this, or I want to show it to a customer? I'm a big believer in CYA. Cover your backside. Now when you look at just this pattern, I'm standing and looking at a whole big forest, but I have no idea where in the forest I'm standing. I don't have any reference point. And I'm going to distinguish between when we talk about triggers and reference points. Triggers is when you tell the scope to start drawing. And you can be creative in the use of that trigger to help you catch things that you otherwise wouldn't have caught. Reference points tell you where you are in the pattern relative to something else. So let's add a reference point. Now what I really like this for is when you're dealing with any kind of a transverse design, you might be able to get to the front bank fairly easy to do a traditional compression test, but it's a bear to get to the back. And I've looked at the flat rate on some of those. It might be 2.5 hours. And down where I live, that means I would be charging my customer $250 to $300 for a test that may or may not show anything. They're going to like that. But if I can say, here, Mr. Customer, I have this capture I want to show you, explain to you what it means. It's showing that there's a weakness in XY cylinder. Now I have justification to spend your $300. Or I may find out it's in the front bank, it's only going to take me 10 minutes. So that's what the reference point is for. It doesn't matter where I trigger or what my reference point is. I'm just using an ignition event, spark event. But I don't really care which one it is. I'll show you why in a second. But let's just zoom in and we'll take a closer look now that I have that reference point. How many cylinders do I have in this engine? 4. Is there anything else that this pattern is telling me? Remember what we referenced earlier. If the peaks are not that wide, if they're shorter than what you would expect them to see, and you would suspect a low compression because of an out of time, is there anything in this pattern that would tell you the same thing? When does this event occur? And that's a valid point. I mean, it looks like it's right dead on the money on the peak, okay? But if it were out of time, even a tooth, that would generally be at least 10, 15 degrees variance. So if it were out of time, I would expect it to see way off of that peak, left or right. Everybody with me? So I got a pretty good feeling now. I know that this has got a 54 amp peak to peak. The trigger event, the ignition event, is occurring right at top dead center where it's supposed to be. So I don't think I have any issues with cam timing. I can use now that ignition event and use the firing order of the engine that if I do have a weak cylinder, I can identify which one it is. Just say that the hump on number 2 was low. Now I know exactly which one to go for. Maybe I don't have to rip the plenum off and start checking the back bank. Maybe the problem's up in front. Ignition timing is indication that that's okay. Now here's one I took from a 2005 Pacifica. Is that good?
No.
No? Why not?
There's some high and some low.
So when we're looking at the forest, there's some discrepancies there. Are the discrepancies uniform?
Yes.
Do they repeat?
Every 5th one's low, every 6th one's high.
Okay. Now again, with a PC-based scope and some of the handheld scopes, I can take that one and get a lot closer. And there you can see what you guys pointed out. The 5th one is low, the 6th one's high. So these are all drawing equal amounts of current. This one not so much. Could that indicate a weak compression in that cylinder? Okay.
And then there's the high one because it takes more to get that motor turning back again. So there's really nothing wrong.
Well, let's think about it. What he's asking is that right after the low one, there's a high one. Took more current draw. Okay, so why would that happen? Well, how do most systems identify a misfire? By the crankshaft, right? By speed. So when I have a weak cylinder, it doesn't tweak quite so much. And it did slow down. It slowed down, a few microseconds, not an appreciable amount, but it did slow down. But now that it took a little less to get that one through, the engine's momentarily slowed down, and it's going to take a little bit extra effort to get it sped back up again. Okay. Could there be anything else wrong here? Well, we'll see. Now, again, the 3.5 is a transverse V6. It's 246 on the front. I just grabbed number 4 because I need some type of reference point. I want to see where that low peak is. I just got lucky on that one. Happened to be number 4. But now if I want to do any more traditional testing, maybe I do want to throw a compression tester in there or a leak down tester or something. I know I want to look closer at that cylinder, don't I? How long do you think that test takes? A few minutes. A few minutes. Great comment that came from Auburn. One of the guys there, he fires up, most of you might fire up all your laptops and tools when you get there in the shop in the morning. He includes his scope. Scope's always on and ready to go on his workbench. So if he wants to run a quick test, it's just a matter of grabbing the leads and hooking up. And I'll be the first to admit, sometimes I've had a problem in the shop and going like, boy, the scope would be really great for this, but damn, I got to pull it out of the box and I got to start the computer and I got to hook up all the leads. And so if you have Alternator set up and running, then you don't have that problem. A little later on, I'll show you a test that you can use on every car that gets into your bay. Might make you a little bit of extra money and certainly make your customers a lot happier with you. We're still talking about engine mechanical conditions, still relative compression. How many of you guys are using the first look tailpipe pressure sensor? Okay, all this is a piezoelectric crystal that reacts to changes in pressure. How many of you guys remember the dollar bill trick looking for bad exhaust valves? What did we do? Take a dollar bill in the tailpipe and it was like, blah, 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 and when it hit that bad cylinder, what happened? It gets sucked up into the tailpipe. So we've got pressure changes going back and forth out of the tailpipe. And all this sensor is doing is reacting to those pressure changes. How many of you guys are IATN members? Okay. Go to the tools and equipment forum. Some guys are making their own. They're getting a $5 piezoelectric sensor down at Radio Shack, and they're buying a little baby bottle and an old tire valve stem, and they're making their own pressure sensor. And when you stick it up the tailpipe and you crank it over, this is similar to a pattern that you might get. Is that a good pattern? Personally, if I've never worked on that car before, I have no idea. This is the first tailpipe sensor or test I've ever done. I have no idea. Is there any uniformity to it? Yeah, I'd say so, right? Every other one is up there. Every other oddball or odd. So now I want to take a look at what I'm testing. What about the engine and the system that I'm testing? Well, let's take a look at the firing order. Anybody see anything now?
One bank is low.
Yeah, one bank it looks one way, the other bank looks the other way. So however the tailpipes, the plumbing might be run, or the exhaust manifold might be designed, can affect the way that this pattern looks. Now if I saw one of these, of the three, chopped in half, that might throw a flag up that needs investigation. Here's another example. Is that good or bad? Looks fairly uniform across the tops. Again, we're doing relative compression. I'm starting a drivability diagnosis, maybe a PO300. And I just want to go quick right offhand. Do I really need to worry about the engine's mechanical condition, or can I move on to something else? If I saw that, I'm moving on to something else. We can look a little deeper though. I'll add a reference point. That's kind of odd. 1, 2, 3. 1, 2, 3. This is either a really old Geo or it's a DIS. So no matter. Well, we're going to block it off as a 6-cylinder. Now I'm triggered. Now remember, I'm looking at a tailpipe event. And I'm triggered off the ignition. So let's just say that's number 1. Halfway through would be number 1 again, but this would be top dead center of what? Top dead center compression, top dead center exhaust, right? So I'm starting at bottom dead center, working my way up top dead center. This would be actually the section of that waveform associated with this cylinder. Now the first look comes with a little chart that tells you if you have a 4-cylinder, you move to the left 2. If it's a 6-cylinder, you move 3, whatever. Then I can never remember that. So what I do is I take a capture and I take it out and put it in my Windows Paint program, and I add some reference lines of my own so I can say this is 0, 180, 360, you get it, 720. There are some programs now you can get through AES that will do that for you. I think Bernie's scope, it's automatic. You know, good, we'll lay it out there. There's some other overlays to go with the Pico that you can get, that you can count off the degrees as a reference point on any pattern you want. I have paint. It works just fine. And then you think about it. There's a lot of discussion here in the places I've been so far this year on the future of our industry. I work with a lot of guys, like I said, nobody ever used a scope. And they were good techs. I mean, they could do the brakes and the water pumps and timing belt jobs, and they could do it very quickly and do it correctly, and they made money at it. But if you threw something in there that made the car run not quite right, they couldn't fix it. They couldn't diagnose the problem. As long as everything stayed normal, they were fine. And I think that the people who can are guys like you, that 10% we were talking about before, who stay up to speed on what's going on, who learn new techniques, keep up to date with the changes in the technology. They're the ones who are going to have the future in this business. I think you're going to see that evolve. It's a thinking man's game. Neat thing about the first look sensor, if I do find a low peak, identified a weak cylinder, it's got to be one of two places, right? Top end or bottom end. What if I move that first look sensor to the oil fill tube? What would I be measuring there? Crankcase pressure. What affects crankcase pressure? Isn't that the pistons moving up and down? Do the valves impact that? No. So what you're seeing here, that's the pulses in the bottom end as the pistons are moving up and down. If I had weak rings, I would find one of these smaller than the other. If I see them like this and they're all uniform, but my first test showed a weak cylinder, what can I go back and tell my customer? We need to take the head off. You got a problem upstairs. Again, how long do these tests take? Not long. Not long. How long would it take you to do a traditional compression or cylinder leak down on a transverse V6? To find the same thing. Okay? Here's another pressure. Now this is using a pressure transducer. There's a difference. The sensor reacts to change but does not physically measure how much it is. The transducer physically measures how much pressure it is. And there are a bunch of them on the market. I personally use the Pico WPS 500 because the one transducer will cover ranges from intake manifold vacuum to 500 psi. Bernie makes the set. I think Snap-on has them. You can still even get the PV350 Fluke transducer from companies like AES. That will do just fine for you. And what we're looking at here, this is the injector event. That's just my reference. And this little red squiggly line here, that's intake manifold vacuum. Now the tailpipe can help me trigger on exhaust sealing issues. The intake side can help me track down intake sealing issues. Do I see anything wrong with this pattern? Anything stand out for you?
Flat spot.
Well, here's one right here. One right here. This one here, did everybody agree this little section here kind of looks like what I would expect to see normal?
Yes.
Because it's pretty repetitive. Not always the same amplitude, but the 2, 3, you know, the 2, 3, 2, 3, but these little flat spots here, that's an issue. How many guys are still using manifold vacuum gauge? Us old guys, we were brought up on those things. I still got mine, that really big fat gauge. You can still find them on the tool trucks. We actually use them for measuring carburetor fuel pressure, the old mechanical fuel pumps. Okay, and if you were looking at this as a manifold vacuum gauge, what would that needle be doing? Okay, and we've only got about an inch variance. Okay, so help me out here, you older guys. if you saw an intake manifold, you saw your manifold vacuum gauge bouncing with just about an inch of movement, what would you be suspecting? This intermittent miss or sticking valve. So what I'm saying is you can use this tool, but you're still a thinking man. And I included in the handout a little chart of standard manifold vacuum gauge readings that you can use as a reference in your toolbox when you're looking at your intake manifold pattern. I also want to point out right here is that I used the WPS. I bought it for the in-cylinder testing that I'm going to show you a little later on, but I don't like buying stuff that I can use for just one thing. I'd rather get as much out of that tool as I can get. And this is just one example of something else that you can do with that same transducer. Now, again, I'm triggered on the injector event. And I've got the firing order laid out. It's actually, I'm triggered on number 2. This is the number 2 injector. Firing order 153624. So I want to find out which of these little squiggly lines is associated with that cylinder, so I know where to look for the intermittently sticking valves. Now, so do I use this pattern, or do I go 360 out of phase and use this count? Let's give a reference. This is showing the cylinder, in-cylinder pressure, so the peak of the blue trace, that's top dead center of compression. There's my ignition event occurring just before that point. The injector event's actually occurring closer to TDC of what? The exhaust stroke, right? So wouldn't that one be correct? What happens right after TDC exhaust? Starts coming down on the intake. So if that's TDC of exhaust, and it's moving now towards BDC, wouldn't that be the intake portion associated with that cylinder? What if I triggered on number 2 ignition? Then I'd have to use that one, wouldn't I? Because I would be starting off TDC on the exhaust, BDC on, and this is not going to be accurate because it's split up more than in 4s. But I'm going to be 360 out of phase if I use the ignition event as the trigger. Do you see where I'm going with that? You see what you have to think about depending on what your reference point is. Okay? Do events happen by themselves? Of course not. There's always some overlap. And this is just showing you how that intake pulse is actually being overlapped by other cylinders. Because by the time I've got that one intake valve about halfway open, another one starts to open. Right? And the more cylinders I got, the more of an overlap I'm going to have. Now you can use that first look sensor as well, or you can make the baby bottle version. And you can use that to look at the intake manifold vacuum. Just keep in mind you're not going to measure the actual amount of vacuum, but you'll be able to see how much is bouncing around. Now, here's another thing that's a really good use for the scope. We're still talking about mechanical condition of the engine, and that's looking at the in-cylinder pressure. You determine that you have to do a traditional compression test. And I can either pull out my Craftsman Sears mechanical gauge, or I can pull out my transducer. The traditional gauge, I'm going to watch to see how quick it comes up to its peak pressure, and then I have a peak pressure, right? But I don't know what's going on the rest of the time. Once I hit that peak, I can keep cranking, and I don't know what's going on after that. If I put a pressure transducer, I can watch the pressure through the entire 720-degree cycle. I'm going to see what's happening on compression, intake, exhaust, and power. Okay. And you can see there's a lot of valuable things that you can see in that. I mean, if you're going to go through the effort to do the compression test anyway, might as well get as much information as you can, right? We're going to focus, excuse me, on the cranking compression first. Again, I'm going to pull out my paint program. I'm going to add my degree references. And I have it outlined in your handout how I do that with the paint. It's really easy. When you copy the picture into the paint program, you'll have a set of cursors. And if you lay the first cursor at the top of the peak, you look on the screen, you're going to see two numbers. They're the pixel coordinates, just like on a graph. And the first one is the vertical coordinate. So I write that number down. Then I move the cursor over to the one on the far right. And I write that number down. I subtract the two. I get a total distance, pixel distance between the two. You want to find out what the 180 degree marks, just blow that up by 4 and add that to where you started off, and you start marking off your lines. You want to be a little finer than that, divide it by 8, 16, whatever you want. Okay? So we're starting off with top dead center. Compression. The piston's moving down. Now, what is this line here? What do you think that represents? That transducer had to be zeroed, right? What's it zeroed to? Atmospheric pressure. Whatever is it right here in the room right now. This is atmospheric pressure. It's going to show up as 0 on my scope scale. Isn't every tool that you use referenced to atmospheric pressure? Sure. But here's an interesting concept. Let's see, this works on, help me out here. Was it Boyle's law? About the gases and volumes and pressures? I'm not that smart. But it seems to me if I start off, the piston's at the bottom of its stroke, I've got all this volume of air now in the cylinder. The intake valve closed just after BDC, right? So now I've got a shut container, and I'm going to move the piston up. And as I change that volume, the pressure of that air is going to change, going to increase, right? Now this is not running. This is just cranking the engine over. As the piston moves back down, isn't the reverse happening? As the volume starts to increase, the pressure decreases. So if I get to the same bottom dead center as I started off with, shouldn't this line be straight? What is that little dip?
Isn't that the other valve opening?
Well, this is just running. I want to know is, if I have all this air in the cylinder, and I have the same air in it when I get back to bottom dead center, shouldn't the pressure I started with be the pressure I ended with? In a perfect world, is that cylinder perfect? Is there always a little bit of loss? Okay, that's what you're seeing. We're going to lose a little bit, okay? So that when I do get to the bottom, I'm actually in a slight vacuum. And that's no big deal, but it is a key. What if I had a problem with the cylinder where there was a significant loss? What do you think that's going to look like? Really big, right? Really big indicator. What if I'm looking for an intermittent sealing issue? Do you think I could watch that? Go normal to not normal, back to normal? Okay. Sure. Word of caution though, a lot of these scopes, as you've seen me show already, you can zoom in on certain parts of the screen. If I looked at this screen and all I saw was the capture, would I think right off the way that this was bad? This had a problem? Doesn't that look like a really deep pocket? Okay, but it's not. It's the same as this one. It's just a matter of the zoom function. I'd have to pull out the cursors and measure it, and you find out it's not that big a deal. So don't let that throw you off. Okay? Don't look for things in the pattern that aren't there. When the transducer is 0 to atmospheric, here we're talking about another way you can tell if there's a significant loss. If you split that compression peak in half, it should be almost a mirror image in the two halves. It should be symmetrical, not perfect. Okay. Anybody see anything different with this one? How does this pocket look?
Very long.
And so now, but there's always one other thing to go along with it, right? What about the peak in front of it? You see anything weird about that?
It's like squished from the right.
Does it look like it's kind of leaning over? Because when we got to the top, we compressed the air charge. When we compressed it and stay there, we lost some of the volume. So now the pressure is going to change much more rapidly and drop into vacuum. And of course, not to mention that you could actually measure the same cranking pressure that you would with your traditional gauge. You got all the information right there. What I really like about this test, well, let me throw this in first. A little food for thought. This is a courtesy of Matt Fanslow. Notice that this is still one 720-degree rotation. What's wrong with this picture? Is that? Who said that? What did you say?
Exhaust valve didn't open.
Exhaust valve didn't open. See how we came to that conclusion? This TDC of compression, this is the next TDC of compression. What's in the middle? TDC of exhaust. Okay, I have very little pocket, but here the whole thing actually dropped below. And all of a sudden the pressure starts to build again. What happens at TDC, exhaust?
Pushes out. Valve shield.
Well, the exhaust valve is just starting to close right after. But what happens with the intake? The intake opens just before, right? So as soon as that intake valve opened up, all that pressure went away. And you're right, this exhaust valve is not opening. Remember that early relative compression with the starter? The low and the high? That's exactly what Matt had. And like any of us, he went after the low peak first. But when he tested the cylinder with the in-pressure transducer, it looked normal. Compression pressure was normal. The pattern was normal. So he went to the next one in firing order, the high one. And this is what he found. When that engine was cranking for that one moment in time, there were two cylinders on compression. Okay, effectively. And that gave that slight peak, higher peak in current draw. This is the real power of this particular test is by actually plugging it in and running the engine. Okay, I have everything referenced on this particular one. I've got the spark event, the injector event, and then the cylinder event. Let's just take a look at the cylinder event. Okay, now we have a running engine. All the other cylinders are running while I've got my gauge in this one. Now the WPS comes with special hoses to use. If you use a PV350 or you adapt another sensor and you're using your traditional compression gauge, just like we did the old mechanical running compression, you got to take the Schrader out, okay, so you don't get a peak. We're going to start off first. What are we referenced to? Atmospheric pressure, okay? We're coming up on top dead cylinder, top dead center of the compression stroke. Again, this is a running engine, so I'm going to expect that number to be lower than what the cranking compression test was. Now I'm going to move down to the exhaust pocket. I'm coming down to TDC towards BDC on the power stroke. And what happens just before BDC? Then the exhaust valve begin to open. Look very carefully here at this part of the pattern. Notice how it's nice and smooth, and all of a sudden that changes right there. See how it abruptly starts to rise? That's when the exhaust valve opened. Okay. If you see this nice and smooth, just nice and round, then you've got a problem with the exhaust valve. Okay. Now here again, I'm measuring pressure. The exhaust valve is open. I'm heading back up towards TDC. I can measure this. This is particularly one measured at 1.8 psi. Of course, I want to make sure my transducer is properly zeroed. But what am I measuring there? Spot pressure. Do you think I might be able to use this if I suspect a clogged cat? What if I have a dual cat system and I think one's messed up and the other one isn't? Could I compare bank to bank? Okay, and ideally you should do a snap throttle and watch that pressure plateau. If the exhaust is clogged, you're going to see it rise rapidly. Okay. What about the little squiggles? They mean anything to me? What's going on in the exhaust manifold?
Turbulence of the air.
There's other turbulence, there's other cylinders dumping in there, right? So that's what I'm seeing there. Same with those squigglies we saw on the first look sensor. There's more than one cylinder dumping at the same time. Okay, so I get the TDC, the intake valve's open. Now I'm coming down on the intake stroke. And if I mark off those lines, and I'll show you in some notes here in a moment, but I can use these ramps to help me gauge cam timing. Now, if we suspected there was an issue with cam timing, first we could see it in that ignition event, right? But what about multiple cam engines, or VVT? This will let me see both cams for that cylinder. What about here where I'm measuring now with the intake? Got a minus 10.6 psi measured. What am I measuring? Manifold vacuum, right? Would be, if I had a map sensor on this engine, wouldn't that be what it'd be reading? Isn't that the absolute pressure? And then we get back to TDC. Now, just like I showed you with the starter, I can use this as a gauge of timing, because is that crank position going to change? Is everything referenced to where the piston is? And that's not going to change. Everything else might, right? The cam sync can change. So if I see that this ignition event occurs over to the left of that piston position, it's got to be advanced timing. That's what I'm going to be looking for. Conversely, if it's moving over to the right, past the peak, happened after TDC, it's retarded. And I can use those same references to the other lines that I lay out and show you here in a second. What if that exhaust ramp occurred before it intersected? We're just going to use these marks. Like you can see the little teeny little dimples there on the ignition line. Isn't that going to be our 180 marks? Right? So we're just going to assume that, okay, that's going to be BDC of the exhaust, start of the exhaust stroke. If this ramp were to the left, what would that cam timing be? Be advanced. Okay. What if it were to the shifted to the right? What about using it for variable valve timing? Yes, sir.
Actually, that was going to be my question. For variable valve timing, would that, if you're revving it up, would that move?
It should.
Obviously not the spark line, but the other
Yes.
pattern? Would
Yes, you can see that. You'll see the ramp move. Okay. So what is referred to is you're going to be looking at this portion right here. This moving here. And if you wanted to test the VVT, you could use the bidirectional control to command it off and on to see if it was working as it should and moving as far as it should. I could take my paint cursors and measure the amount of degrees it moved, okay, to compare. How about for timing belt or just timing chain wear? If I had a lot of slop in the timing chain or a failed timing chain tensure, what do you think the ignition event would be doing? be bouncing around, right? And I'll be able to see that. And that's the one thing that I wish I could do more of. And we'll do when we do some of the scope work that we do in the live webcasts. Looking at a static pattern on the screen is one thing. Watching it run in front of you is a whole lot better. Here's an example, too, of how this can be used. We kept talking about intermittent sealing issues. Now, this particular capture's got 8 minutes worth of data on it. One screen. Another thing I like about the scope, I can set a trigger to look for a problem, turn the scope on, start the car up, and then go do something else. Because I've given the scope the parameters of when to start drawing. Okay? And on some of the PC-based, even the handheld devices, you can store a lot of information on one time that you can go back and look at later. This was dealing with an intermittent 306 code, only cold. Do you think they found what the problem was? What you're looking at here is the peaks of those inline cylinder pressure transducers. It looks like a smear, but I could open it up so it would look just like that. And all I'm looking at are these peaks. You could also set your scope up to use one of your cursors, lay it on top of the peak, and then let it run and watch. If you have an intermittent sealing issue, you'll see some of those peaks drop below the line that you set. And I think, what's the running compression? 40 pounds, well, 45 pounds is going to result in a dead hole, because that's not enough to generate compression or combustion. Okay. Here's a little quick review for your note page on the basic elements of the pattern. A, of course, is top dead center of compression. That's always a good reference point, because no matter what happens, that's always going to be where the piston's at the top of the cylinder. Always. As I move down, nearing bottom dead center of the power stroke, the exhaust valve is going to start to open, and that upward ramp should occur right about BDC. Should be right about the middle. Give or take 10 or 15 degrees. If there's a timing issue, if we're off a cam, a tooth, you're going to see that shift at least 10 or 15 degrees more than what it should be. So you'll see it. It won't be a question of whether it's just a little bit. Okay, now we have the exhaust stroke. Heading back towards TDC at C. Because the intake opens while the exhaust valve is already open, you're not going to see exactly when that event occurs, but the ramp is still something I can use as a reference. The middle of that ramp should occur about 20 degrees after TDC. Again, if the intake cam is off for whatever reason, it's going to be a noticeable change, left or right. Okay, then I'm going to get to D, BDC of the intake stroke. We close up, and then we just repeat the pattern again. If you want more information on this, the Jeep story is on our website. It's also on the Alternator site. It's called The Wrangler from Hell. It goes through the diagnostic process they use to find the problem. Bernie's got a ton of information available on the ATS website on how to use an cylinder pressure transducer. In my mind, Bernie is the guy that I know he was the guy that cracked that egg open, because he's been doing this for a long time. You know, just like some guys did the current ramping years and years ago. I know he was among the first for that. Another common use for the Labscope is to check the relationship between the cam and crank sensor. Before we had in-cylinder pressure testing, if we suspected there was a timing issue, we had to look at the sync between these two. Did they line up? Who knew? There wasn't any rule that said this is always going to line up this way that you could apply to every car. So the only way you could do that is if you had a known good pattern. And in the early days of us guys that were using the scope, if you wanted known good, you had to get them yourself. The one thing here I would interject is that if you're not using your scope routinely, take the time, every car if you can, to just capture something. Hook up and test something so that you're familiar more and more with what known good looks like. And for setting up the capture to save you time later on when you need it. Just like your scan tool, don't wait till you got a broken car to break out the tool and try to use that, learn how to use that at the same time you're learning how to fix the problem. These, however, are becoming much easier to find. ITN has got quite a database now of reference waveforms. Alternators does, wavehook.com does. These references are in your handout. Even Pico headquarters in the UK has some. A lot of the tools have them, the handheld tools have them built in. They even tell you where to connect the leads. Okay, some of the I think Bernie's very user-friendly. The in-cylinder pressure stuff, he's got it messed up now where Bernie's software will tell you what's wrong after you've got the capture. You don't even have to learn how to interpret the waveform. My Pico, not so much. I have to figure all that stuff on my own. Now, here's a little something here to help you think too. You did a relative, and this is a generic question. Just want to see if you can put some pieces together. You did a relative compression test using starter draw. You had your ignition event triggered, and you noticed that the ignition event was occurring way to the left of the peak. So you know what? The timing's off, is advanced. The timing's off. So you go to take a look at the cam crank sensors, and they're in time. Where would you go?
Cam just move forward against the gear.
Well, say that again.
If your cam crank correlation looks okay, but pressure transducer shows you incorrect timing, then it's actually the gears on a cam probably spun.
Everybody hear that? Now, if I go with a cam, and I say if I go with the cam, I'm going to see a variance. Well, I see a variance in that peak because that'll change the compression, right? Because the timing is now off. But I can have good compression if the crank spun, right? The crank doesn't care. TDC is TDC. But if the trigger for the crank sensor is on that flywheel or on that harmonic balancer and it's spun on the crank, it hasn't lost its relationship with the cam, has it? And the ECM says, okay, that's when I need to fire it, and I'm going to fire it then. Okay, see what I'm saying? Number one, it's a thinking man's game. That was a good thought. But it was, you took two tests with your scope and found out why this car was running kind of ragged and didn't have any code set. What would the scan tool tell you? Cam sensor sync? Yes. Right? Here's another example. Now the Hyundai 2.4, I knew this had an issue. There's no injector pulse. There was no ignition event. I mean, I think most of us would go after the crank sensor to see what was happening. But it's the chance for me to go ahead and grab a capture, get a little more practice with use of my scope, and maybe I might learn a little something. And this is where I got in the no start. Well, I know for sure now I've got a problem with the crank sensor, right? I mean, it seems to be getting voltage, but I don't see anything being pulled to ground. I wonder, could I do a voltage drop test on that circuit with my scope? Am I doing a voltage drop test? What's the scope reference to? Reference to ground. Okay. But if you do think of it that way, make sure you understand where you put your leads. When we did the voltage drop webcast, we encouraged you to do your voltage drop test as close to the component as you could get. If you didn't, there was a whole strand of wiring that you were missing, right? Well, that's the same thing here. I've got the leads placed at the harness connector, but it's way at the top of the engine, because if you've done one of these 2.4s, the sensor's not the easiest thing in the world to get to. Okay? And there it's hiding. I mean, you gotta get the belt off just throughout the harness, and someone was telling me last night this is very common when the timing belt's replaced by someone who doesn't know what they're doing. So, put it back in, get a nice good waveform to use as a reference later on. But now I can also check the electrical integrity of the circuit, right? If I look at this ground point and I zoom in on that, would it be the same as doing a ground side voltage drop check? What would I expect to see there? Really? Could there ever be an exception to that? Where does the sensor ground? Ooh. Anyone familiar with the term floating ground?
Yes.
Okay, what's a floating ground?
Floating ground is held above vehicle ground.
Okay, and that's to prevent interference, right? So if you're checking something that's grounded to the module, then it's going to have a floating ground, and you may see as much as, what, 0.7 as a reading. If you're not aware of that, you may go like, ooh. It also depends on where, if you're doing a voltage drop test, where are you referencing your measuring tool, right? What if I hook my multimeter or my scope to the ECM ground? Would I get now a voltage drop that should be closer to the 0.1 or 0.05, the normal of what I would expect to see? If you have a sensor that you want to read and get a good pattern on your screen, an accurate pattern on the screen, if it's a floating ground, you must reference your scope to the same ground. You'll get the same shape if you reference it to chassis ground, but you won't get the same amplitude. And that can make a difference. The Ford synchronizers, if you look in the TSBs, they actually tell you, you want to see if you've got a bad synchronizer based on the 3 cam crank sensor that they had. They gave you a pattern waveform to compare to whatever you got. And you could see if it was in time, you know, if that was causing your problem. But if you didn't hook to the same grounds, especially the cam sensor wouldn't look right, because it's one of those AC type sensors, signals that you got. Okay. Anybody ever see one of these ignition systems that makes up their own cam sensor signal? There are a few. Saab, Saturn, the compression sense ignition. There's no cam sensor on the car. You can get a cam sensor code, but there's no cam sensor on the car. It's because the ignition module creates the cam sensor signal and sends it to the ECM. That's what that looks like. Moving on to fuel system testing. Now again, a lot of the techniques that I'm showing you are just a few of the ways that you can use the scope to speed up your diagnostic process or get you diagnostic direction. If you're dealing with a drivability issue, especially one that doesn't have a code, at least I always wanted to see what could I do to very quickly gauge the health of the ignition, the fuel, and the engine mechanical. And we talked about the mechanical side for the first part. Let's talk about the fuel side. One screen. Red traces the current of the fuel pump. The squiggly little green line is using that same pressure transducer that I've used so far, but now I'm sticking it right in the fuel rail and placing my fuel pressure gauge. That's the nice thing about the Pico transducer. It can be used for air or hydraulics of any kind of fluid test. And then I've got a reference. In this case, I'm just going to use an injector. Let's start with current. Using that scope, I can zoom that thing open and see what's going on a lot more closely. Again, I like looking at the forest and not the trees. Is there anything out there that stands out? Well, first I've got kind of a curve to it, don't I? Okay, this is a running fuel pump. Is there an AC component to DC voltage coming out of the alternator? Sure there is. So it's not going to be unusual when I'm zooming in this close. Notice you don't see it so much here, but when I start zooming in, I'm going to notice that. And that's all I'm seeing is the AC influence on the DC voltage to the fuel pump. Okay? Now notice I do have a couple of weak points. There's one, then there's one. There's one, there's one. And they repeat, don't they? They still have a pretty nice sharp edge to them though. And think about what it is that I'm looking at. I'm looking at the current peaks inside this fuel pump motor just like I can any other motor, and the amount of current it takes to turn that through. I'm looking at the current going through a brush, through the commutator segment, through the winding, and then back out again. Okay? Now if I saw any of these that were gone or really flat or really hashy, wouldn't that be an indication of severe wear between the brush and the commutator strip? The fuel pump may be operating today just fine. Would I be out of line if I showed that to my customer and said, you're good today, but this thing's near its end of its useful life, you might want to think about replacing it before you guys stuck on one of these wonderful highways you've got around here. I think the last time I was up here, I ended up in Brooklyn. I don't know if I want to get stuck there where the fuel pump decided to crap out. So you could use that as a selling point. You wouldn't be doing your customers a service. If anything, you're doing what your profession requires of you. Just like the doctor. Everything looks good today, but I did see something on the x-ray that could be a problem down the road. Maybe we ought to head it off now. Right? No difference. Since I have a repetition identified, I can use that to divide it up. Every 8th segment, that pattern repeats itself. Well, that kind of fits in because that particular fuel pump has 8 segments on this motor. And we spoke briefly about this before, but let me hit this again. In a motor, what impacts the current draw? Not just the electrical, but the mechanical, the load. That's on this end of the pump. Is it possible for you to have a full tank of gas, but a fuel pump that's dry? Sure. Aren't they in a well? If the inlet screen is clogged shut, I can have all the gas in the tank I want. It'll quickly suck that well dry. Yeah. In that intermittent, driving down the road, start sputtering like you're running out of gas. You sit on the side of the road for 30 minutes and you can drive a while again before you run out of gas again. So if I want to make some more use, not just the electrical health of this pump, but if I want to get some diagnostic use out of this, I need to take a few measurements. I'm going to measure the time it takes for one segment to complete, and of course I'm going to measure where the current draw is. In this case, measured current's about 5 amps. Is that out of whack for a fuel pump? Not really. How are you going to know that? Because I have my scope up and running on my workbench, and I've been taking measurements with it on known good cars. I have a feel for what's range is good and what's not good. If I saw it pulling 10 or 12 amps, my eyebrows would be going up in the air. Conversely, if I saw it drawing only a couple of amps, again, that to me would be like not normal. The time it takes for it to complete one turn can be turned into its revolution or its RPM. This one's running at about 6,400 RPM. Again, is that normal for a fuel pump? For most. So there's a good baseline there. Again, if I see one that's spinning along at 12, I'd be wondering. Or if it's struggling on about 2,500, I'd be wondering. If I notice that I have a really high pump speed, but the current is low, doesn't that mean that the pump isn't working real hard? pumping air. Yeah. Anybody ever have a nose start get towed in? It's got half a tank reading on the gauge, but it's out of gas. Yeah. We wonder if the fuel pump's turning. We don't hear it, so we get out the big rubber mallet and start beating on the gas tank. You know, on newer cars, you can screw the pump up that way. If I throw a low amp clamp, I don't even need the scope, just a low amp clamp in my multimeter on the fuel pump circuit to see if any current's running. I know whether the pump's running or not. What about the other side of the coin? What if there's a low RPM, but the current draw is much higher than normal? The pump's working its butt off. All customers change their fuel filter every 30,000 miles, don't they? I bet you guys had to cut yours off with a torch, right? Oh, no, excuse me, that's the mini ductor. Use that. If the pump speed is normal, maybe a little low, but the current draw is lower, could that be an indication that I have a resistance issue in the circuit? Never seen that happen, right? The connector's corroded in the harness underneath the car. We get that in Florida if you live near the beach. The Daytona Beach is like a really popular place where you can still drive on the beach. And we watch tourists every year park their car and then they go off checking out the boardwalk and they come back when high tides come in. And now their car is up to the door handles in the Atlantic Ocean. But simply driving on the beach is enough for that salt water to start corroding. Again, not on every car, but if I'm just doing a basic, trying to get diagnostic direction idea on the fuel system, every 10 psi of pressure usually results in 1 amp of current draw. So earlier I got 5 amps, about 50 psi. I've got a rough baseline that I can compare to specs. I don't have to guess though, because I can actually measure the pressure. That's what we did. Right. There. Now with my transducer, I don't have to use that anymore. If I'm going to hook my mechanical gauge up, I might as well hook this up. Now before I get to pressure with the WPS, let's take a look at something that I don't have that yet, but a scope is only limited by your own imagination. I had an F-150 that was giving intermittent misfires, running kind of ragged, had been around the block several times and nobody was having any real luck nailing down the problem. So they asked me to take a look at it. Now I'm not going to lie to you, it took me a little longer than 10 minutes to fix this car. But I thought, well, maybe I need to do an injector drop. I suspect an issue maybe was something in the injectors. Well, if I wanted to do that the old-fashioned way, what would I have to do? I have to pull out my little tool, get to the injector plug my tool in, hook it up to the battery, hook up my fuel pressure gauge, prime that, then hit the button and start recording numbers and repeating that. And then you start comparing the numbers to see what the drop was. And gee, that's a lot of work. Ford was kind enough to stick a fuel rail pressure sensor on some of their vehicles. And that's what you're seeing here. I'm just going to the same sensor wire that tells the ECM what's going on. Now, I don't know what the pressure is, but I know I'm going to look at this and see, is this normal? Is this telling me something, or is this okay? I have a reference, so I know that this is all the cylinders on one screen. Let's look at it a little closer. Again, that's what I like about paint. I can move that stuff around any way I want to. I'm on the #1 injector. So right when the #1 injector opens and closes, I've got this drop. You see that? Nice, fairly smooth line. There's the drop. So right off the bat, all the drops are relatively uniform, aren't they? But 1, 3 looks kind of nice, but I get to 7, and that looked really nasty. 2, again, fairly smooth. 6, 5, nasty. 4, pretty smooth. Now 8. What's common to the ones that are nasty?
Same bank.
They're on the same bank. Now in relation to where the fuel's coming in, where are they? They're on the tail end, right, of this returnless system. So I'm thinking to myself, you know what? I think there's something not right with the flow. It'd be like holding the injector up out of the rail and watching it, splash out all nasty looking. But that's a lot of work. You know, I'd pull the rail and get up my paper cups, and so I pull the injectors off. I don't know if you can really see it in this picture, but there's no filter in these OEM injectors. That's the way they come. So if it got past the fuel filter, it got to the injectors. And we knocked them out, and you can see the crap. You know, I didn't have some of the stuff that G has. I couldn't run them through any cleaner. But the place I worked for at the time, we were very good standing behind what they sold. So the boss said, just put some injectors in it. Sounds good to me, boss. This is what the pattern looked like afterwards. Really nice, clean, uniform. The little spikes here, if you become more accustomed to scopes, you get what's called a little bit of noise, especially under hood. Under hood's a very noisy place electrically. Ignition's firing and injector's firing. Fluorescent overhead lights can cause noise in your pattern. The Pico's kind of cool because I can apply a filter to that pattern and breathe some of that hair out of it and clean it up, make it look a little cleaner. Okay? But knowing what it is, I'm not too concerned about it. What I'm looking at is nice and smooth.
And you took that out of the pressure transducer, right there on the rail?
Right there, the OEM fuel rail sensor that the car came with. Here's another way to do it. The first look sensor I told you about earlier, okay, reacts to pressure changes. It's a piezoelectric crystal. One morning, a fellow was working on a return type system, and he noticed on the fuel rail there's this funny little round thing with a vacuum nipple on it called a fuel pressure regulator. And he woke up one morning and says, I wonder what would happen if I stuck my first look sensor to that vacuum nipple. Now think about it. If there's a pressure drop in the rail, that causes a pulse, right? Will that be fed back to the diaphragm and the regulator? Sure. And it's going to cause a little pressure change coming out the vacuum nipple. And the first look guy said, that was pretty cool, but we'll do you one better. We'll make you one that you can actually connect to the fuel rail. That's what this one is. Still a piezoelectric crystal, but now I'm hooked directly to the Schrader. Anywhere else that you would hook your traditional gauge, you just hook this in its place. And you might get something that looks like this. Again, this does not measure the pressure, actually measure it, but it reacts to the changes. The peak is the pressure drop. Is that normal? I don't know. Is it uniform?
The first one's kind of...
First one's a little, but it's not, I mean, it's not like it's way out of whack with the others. Right? I still got 1, 2, 3, 1, 2, 3, 1, 2, 3.
That's just one bank.
Yeah, this is a 4-cylinder. Go 1, 2, 3, 4. Here's a V8. Again, is it normal? I don't know. Let's look at it by the cylinders. All the black are one bank. All the green are the other bank.
One bank's not...
Yeah. Well, that's a good question. Look at all the black ones. Have a peak and then a little hiccup. A peak and a little hiccup. Peak, maybe a little hiccup. But the greens are a little more pronounced, aren't they? But where am I attached to the fuel rail? It really depends on where the Schrader connection is. Will there be some dampening of the pulse as if it's moving further away from the point of pickup? Just like a manifold vacuum gauge. Right? The closer I get to the source of manifold vacuum, the better reading I'm going to get with the tool, right? So it's the same thing with this. And you take that into consideration. But if I'm looking bank to bank, I don't really see anything too much out of whack. Not when I look at something like this, though. Is that different? And that's what I say before. Don't look at the trees, look at the forest. You see something big wrong with the forest, then you can start digging a little deeper. But don't worry too much about minor variances in the individual trees. Was that? Yeah? That's a good question. Why do you think that happened? Now this is the first look, that's the pressure drop. What happened at 5? Nothing. 5 never opened. So didn't I have an extra pressure in the rail when the next one opened? Okay. Remember, this doesn't measure pressure, but the change. And it was a much bigger change. Okay, back to our original capture. Now we're going to focus on the green line. Let's zoom in on that one. Is that a good pattern? I don't know. Let's see. Well, the pressure dropped. In this case, I'm actually measuring the pressure just like I had my gauge there. And that's all coming out pretty even. But what about these funny little squiggles? Are they uniform? Are they repetitive? Yep. It's like every other one, right? Again, not uncommon. One's one bank, one's the other. Where I am on my test port will help me gauge whether what I'm looking at is cause for alarm or not. If they were dirty, if there was a problem with the sticking or restricted flow or something along those lines, would I expect that squiggle to be accompanied by a change in the amplitude, how far the pressure dropped at the same time? That might change my direction, my thinking. And the more you know about how the picture is supposed to be, how the system works, and apply that to the information you have on your screen. Someone mentioned earlier about voltage testing. I'm going to show you some conventional injector testing. Don't hear too much about this anymore, but it's still a very valuable tool. The blue trace is the voltage at the injector on the ground side, the control side. And the green trace below it is the current for that injector. First, I can look at when it was turned on and off by the computer. That's the same pulse width command you see on the scan tool. But if I really want to know what happened, I'm going to look at this point first. See that little dimple there? When you have a metal rod begin to move through a magnetic field, doesn't that alter the magnetic field? Well, that's what you're seeing right there. That is when that injector actually physically opened. If I had a sticking injector, would I expect to see that position change or not be there at all? Could I watch this running to see if that point moved? Sure I could. Same on the voltage side. That little bump there as the pintle closes tells me when the injector actually shut. And I can use that reference point as well. Did the injector open? Well, if it did, I'm going to see that bump when it closes again. If it never opened, there's not going to be any bump. And if I'm not sure, what if I threw up the neighbor or one on the other bank to run side by side with it as a comparison? Okay. Now I can know exactly when the actual amount of time that the injector opened. That won't always be the same as the commanded time. Right? There's the inertia of all the guts of the injector that have to be accounted for. If I want to check the voltage drop, we talked about that earlier, I can zoom in on the voltage trace. If it's a floating ground, I'll probably see something like 0.6, 0.7. But if I see like 1.2, 1.3, I'm going to start looking in the connectors, maybe even the driver, for a problem. I have to remember where I got the leads attached. The closer I am to the injector, the better. Here's another capture, slightly different type of injector, same information though. Here's another great tool, use of the scope. Monitoring the current for all of them at one time. You can use this not only for injectors, what about the Nissans with the coil issues? Was it the Maxima V6? What if you monitor the current and one of the coils starts acting up? Do you think you're going to see it in that pattern? Sure you will. And that's all I'm doing here is I'm measuring the current through all the injectors at the same time. If I have one that starts developing an electrical issue, when do they usually fail? They're either going to go bad completely or they heat up. Now, this is what I talked about before about using your trigger as a diagnostic aid. What if I'm looking for a problem and I suspect there's going to be an issue with one of the injectors falling out and the resistance is going to go up, so current's going to do what? Go down. So could I set my trigger to trigger on the down slope or set it for a trigger level at that current level and then just let it run? And when it starts to draw a trace, I'm going to see that problem. Or vice versa, I can set it for above normal. What if I want to check the resistance of the injectors? Would Ohm's law work for this? Yeah, sure it would. Well, it'll work for motors. It'll work for injectors. What about this pattern? Again, I got a blue voltage trace. Green is the current for the injectors. Here's number 1, 2, 3, 4. 1, 2, 3. What would you think if you saw that on your screen? Where am I picking up my current from? 9 times out of 10, the easiest place is in the fuse box. But does a fuse power more than one circuit? It can. And that's what you're seeing here. If you look closely, this is actually the injector current pattern, that little somewhat of a triangle. And it's there. That's the same amplitude and shape, but it's riding on top of something else. So when this device, whatever that may be, is turned on, and the injector is turned on at the same time, I'm reading total current flow through that fuse. And that's why I get that pattern. So don't let it freak you out. That's when you pull out the schematic and you look at where you are. And if you wanted to get just the injectors, I just got to find out where the brake is and put my clamp down there.
What else was that?
I don't recall. I looked it up when I first saw it. Blame her, it was her car. On to ignition. This is where most of us learn to use a scope, reading the secondary ignition patterns. I will be the first to admit there are guys much more talented than I am, but I still use it as a diagnostic tool the best I can. I want to share with you some basic information to where you can use it for yourself as well. But I'd rather watch any kind of pattern like the one you see on the screen. I want to see it moving, changing. And the ignition pattern will. Of all the ones that you look at, it'll fluctuate the most because the conditions in the cylinder are never the same. Okay? So what I'm looking for when I'm looking at a secondary ignition waveform is repetitions of an anomaly. What stands out of whack, and I see it often. Let's just take a look at the pattern that we're looking at here first. That looks kind of weird. Is that a normal pattern?
Is that a Ford?
Is that a Ford? It's a multi-strike ignition. What does Ford do at idle on a lot of their models? They actually fire the plug 2 or 3 times really quick. And that's what you're seeing here. First time I saw it, I was like, what the hell is that?
Me also.
Yeah. Let's just take a look at the secondary side first. The first part you'll see is the actual dwell time, the time the coil was turned on. And then we move into the firing line. That is one of the first pieces of diagnostic information you can get. The firing line is affected by the gap. And what's in it? How many see guys still check the ignition system by throwing a plug in the wire and grounding it and cranking it over? And they see blue and they go like, ooh, that's good. Is it? No way. I can fire all day long outside the engine. That doesn't mean it's firing inside the engine. That's one of the factors that affects this particular part of the pattern. How much pressure is that gap under and what's inside the gap, in addition to how big it is. Okay. And again, think. If there's more fuel, it's going to be easier to cross the gap. If there's less fuel, it's going to be harder. If there's low compression, it's going to be easy. Think you can do a relative compression off the secondary? Yeah, you can. You get a weak cylinder, it's not going to have a firing line anywhere near as tall as the rest. But because they vary quite a bit, there are a lot of other methods that I've already shown you that are a lot more accurate. Is this a gap? Sure it is. And you remember that straight little line we saw here? Well, it ain't quite so straight. Another power of the scope. It tracks voltage over time. But with a lot of these modern scopes, I can look at it in microseconds. I mean, how long does it take for a plug to fire? 1.5, maybe 1, 2 milliseconds. And we've all watched how fast that is. Now imagine breaking that down by a factor of 10 or even 100 and being able to see what was going on. If you've got a worn cap and rotor, that's where you're going to see it, right here in this line. Because it's got to cross that gap before it gets to the plug. The next point of interest is the spark kV. Spark kV is a measure of resistance. If I've got a high resistance wire, it's not going to show up in firing kV. Don't believe me, put about 8 feet of ignition wire on in place of a 2-foot section and check the scope pattern. It's not going to change much. Maybe the spark kV will change, but not the firing. The spark kV is a measure of the resistance, and not just in the wire. What else affects the resistance? About how much fuel. Again, if it's got too much fuel, it's not going to take as much to light off and keep burning as if it were lean. The burn line is really the most interesting part. That's where the meat of the diagnostic information is. Because here you're looking again, that quick spark arc that you watch on the outside of the car, that's that line. And I'm watching that spark over the amount of time it takes to complete its burn. Again, if it's rich, it's not going to take as much to start. And because there's going to be plenty of fuel left over by the time the coil is exhausted, it's going to stay fairly flat or even start sloping downward as the resistance decreases. Conversely, if it's lean, it's going to take a little more spark kV to start it off, and I'm going to very quickly run out of fuel in the gap. And what happens then? The resistance increases, so I'm going to see it sloping upward. How about the current side? Well, you can do the parade just the same way I showed you with the injectors. Question though I want to ask on this one, why doesn't that second current ramp start at 0 like the first one did?
Coil's still charged from the previous.
Yeah, because we decided to light it off again before all the energy had been used. There's still a magnetic field. There's residual field in that coil. Could I use that bit of knowledge to diagnose some of Ford's cop coils? What if I saw that second pattern starting off at 0? Would that be a problem? Sure, there wasn't enough energy in the first go-round. What happens with those coils? Don't they leak internally in the secondary? Sure they do. What causes that? Every device in the car is made to do a lot for a very short period of time. It's not made to do a lot. Okay? Alternators are not made to charge a lot for long. Coils are not made to put out 50,000 volts every single time the plug fires. When those plugs get real worn, and we've all pulled plugs that you can drive a truck through, what does that do to the firing demand? It makes that coil work hard every single time. The coil overheats, the insulation breaks down, the coil goes away. Another thing with these coils, if you're going to get a good strong spark, you've got to turn that coil off very quickly. It's like 100 microseconds. Anything more than that, and there's an issue with the driver. But with the scope, I can zoom right into that current pattern and measure that if I suspect that's an issue. You guys remember the Pacifica I talked about earlier? The shop that I used to work at called me up and asked me to help him out with his car. Not because I'm a great tech, but because nobody there owned a scope. I did. And their tech help had told them they needed a scope to fix this car. It was originally towed in as a no start. The tech who worked on it, very competent man, found very quickly the timing belt had jumped, the water pump had failed. So he checked the engine over, it looked like everything was still good and tight, didn't suspect any damage to the valves. Put a timing belt and water pump on it, fired it up, ran beautifully. Turned it back over to the customer, and about a week later it came back. Complaining of an intermittent misfire. Mill light was on for a P0304. When he got it back in, though, the car was running beautifully. Compression readings were normal. He couldn't find any problems in ignition or fuel. They did get it to fail once. And when it failed, it was like a dead hole, no question. And he saw some impact signs on the pistons. You use a bore scope. They didn't take the time to look for the first time around. So he told his boss, we need to pull the heads. I think we got a valve train problem. Wouldn't you guys? So far, I would. So he sends it to the machine shop. He says, check these heads. Machine shop said we did a pressure and vacuum test on them. We didn't find any problems. Sealing fine. Cleaned them up and returned the heads. And the boss said, put them back on. That's obviously not the problem. So he puts it back on. They actually kept the car for a few days, drove it, could not get the problem to duplicate, and they returned it to the customer. Back they came again. Now they're working with Identifix and the tech line at Identifix. And they're saying, okay, well, if mechanically the engine's good, then there must be an issue with either the injector dropping out or the coil dropping out. How are you going to test that?
Can you swap coils? Are they coil on bug?
Is that?
Is it coil on bug?
Yeah.
Swap coils.
Yeah, but what if it was the driver's side of the circuit, not the coil?
Scope with the triggers.
You take a scope. You know, that's what they told me. Hook a scope up to it and watch the signals. And that's what you see here. The blue trace is power going to both the injector and the coil on the primary side. And then the traces at the bottom are the secondary, or rather measured at the primary and the fuel injector. And we let it run. And when I was helping him with it, it was not missing. The pattern I showed you earlier, I did that for giggles. And I'll be honest, I missed the hump. You know, I missed it. But the neat thing about modern scopes is that I can let this run and I can store a lot of data that I can then take over to the desk with a cup of coffee and I can start looking for more signs of problems. And I started seeing these pop up. Look at that. Now, remember we talked about the bird line as a representation of the resistance. I would expect the resistance to either decrease, remain the same, or increase, but not go up, down, and sideways all at the same time. What do you think could cause that? Let's see, fuel. Would fuel cause that? If it's either lean or it's rich, right? It's not going to change midstream. So I doubt that.
Water?
What's that?
Water in the gas?
That's a possibility. Yeah, that's a possibility. And I had a gentleman actually tell me he found the wire. The center electrode was actually loose in the body. It was moving up and down as the engine ran. So what happened there? The gap was changing. Okay? The most common, and one you'll see more and more of, is based on turbulence inside the engine. When you have a valve that is not sealing 100%. Does a valve rotate as it runs? Okay. So every once in a while, I've got the valve rotating position where it was not sealing. So all that combustion pressure is trying to rush back out of the valve. As it does so, it creates a lot of turbulence at idle inside the combustion chamber. And it literally blows the spark around. Mac Vanderbrink, and you can tell this is an old picture because this is my first personal scope, just like the one they had up here on the table. And Mac said, you want to see what that looks like? Take a straw and blow on the spark while you're watching your pattern. And I said, well, Mac, I'm not having 50,000 volts come back up the straw and bite me. So I took my blow tip instead. And you can do this too, to see what it looks like. But once I started seeing these in the pattern, and there were more than one, I went back to the tech. I said, you know what? Your gut instinct was right all along. These valves are not sealing. I hate to tell you this, the heads have to come back off. You take them back to the machine shop and tell them they were wrong. And when you do, save the old stuff so I can see it. I came back about a week later, and this is what he showed me.
Oh,
But it doesn't have to be from a timing belt failure. You can have the same thing from too much coke buildup on the valves. That'll cause them to stick as well. And again, this is something with the GDI cars is becoming not uncommon.
Wow.
Okay. If you can't get to the secondary, there's always the primary. You just hook your scope to the ground side. But be careful, if you go to the injector or the primary or any other high voltage output, make sure your scope can handle that. I mean, some of the kickback voltage on a primary coil can be 300 or 400 volts. My scope's only rated at 50. If I put too much into it, it's going to go up in smoke. So that's why they give me this little thing called an attenuator. It takes that incoming voltage and steps it down. In my case, it's by a factor of 10. So if I take in 500 volts, it's only 50 to my scope. And then I can change the scaling on my scope to read the number. Every scope has that. So check with the manufacturer of yours to see what you have to do to attenuate the signal so that you don't blow your scope up. On that pattern, you're going to see it's the same as the secondary, except in the firing line. You won't see the same level there. But the burn line, the one with all the information, the spark line, the one with all the information in it, that's a mirror image of the secondary. Okay, but what if you got a coil that's got 3, 4, or 5 wires going to it? Can I still get a pattern with that? I can with an inductive pickup. And there are different versions of that. If you guys with scopes, you know you have the secondary leads, just a clamp, right? Goes around the wire. I've actually taken a paper clip and folded it up in aluminum foil, and I bend one end of the paper clip up so I can clamp my inductive clamp on it, and then I use the magnetic foil on top of the coil. And I've had a lot of good luck getting patterns like that. So there's a way. Okay. How many of you guys are still using one of these? Can you see that picture okay? I started working for this shop, I don't know, 7, 8 years ago. Never even touched this. This is a computerized VAT-40. Remember I said earlier about keeping your scope fired up on your workbench and doing something nice for your customers? Well, how about a 5-second battery starting charging system test that you can print out and share with them and show them what kind of condition it's in? Not so much for us down south, but I know you guys can have a battery that works just fine on Monday and won't do worth the crap on Tuesday, especially with the colder weather, right? So all I'm going to do is I'm going to hook my scope up to the battery voltage, positive and negative, and I'm going to throw a high amp clamp on one of the cables. And I can test everything in 5 seconds. Let's just take a look at the voltage first. Here we start off right here. A is when I turn the key on. So the key's on. Does that wake up everybody? Is that going to be pretty close? Maybe not 100%. Pretty close to the system draw. I mean, I don't have the lights on. I could throw them on if I want to. I can add more material to it. Now I'm going to hit the key to start. I'm setting voltage to the battery. The term that has been adopted for this is inrush voltage. To me, it's still loaded voltage. Just like you did in the old days with the VAT 40 and you crank things down. Only now I'm using the starter to do it. Now on a VAT 40, you generally cranked about 200 amps or so. My starter just pulled about 500 or 600. Wow. And that's not an unusual number. I know that's not what we were taught to do when we did starter cranking draw tests. But this scope is measuring things happening in microseconds. And when I first send voltage to that starter, nothing's moving. And nothing wants to move. And it takes that much to get that ball rolling. So that's not an unusual number. The same way, looking at the inrush voltage, what I still call loaded voltage, if you get a number of about 8.5 or better, the battery's in pretty good shape. If you want to double check and use the old, then you just go back to the pattern where your current intersected that 200 amp and see where it intersects with your voltage. That will be the 9.6 or better that we're used to. Okay. Now I got these two little humps and then a slight upslope. All you're seeing there is a mirror of what you see right here. What is that?
Started actually cranking.
Yeah, remember the relative compression test? That's the first few pistons coming through compression. And I see that mirrored right here in the voltage. Then right here, it drops off. Now that, now the engine is running on its own accord. And you see that battery voltage that we took out, we're starting to put back in. Right there. Right in this area here. This one didn't take too long to come back up to speed. Typically, you'll see that upward slope take a little longer before it gets up to full charging voltage, which is, of course, what we're seeing here. So I've got open circuit voltage. If I know that's below, I use 12.4. What about you guys? You know, if it's below 12.4, I'm going to charge the battery for a while before I go any further with it. But I know what that reading is because I started right off the bat with it. I can see roughly what the system draw is. I can see what the fully, truly loaded voltage is. I can see what the charging voltage is. And the neat thing is, I didn't stress the alternator or the battery in any way, shape, or form to find out. I really try to support, especially the public side, vocational education for our business. But I still get kind of upset when I walk into one of these programs and I see them teaching VAT 40s. When there are so many more ways to check that system, do it more quickly, more accurately, without potentially damaging the system. A lot of newer alternators, if you're cranking loads on them, you can actually cause damage. You'll overheat them. It causes the solder joints to get weak, and it may not fail right then and there, but a month or two later, your customer's showing up at someone else's shop with a bad alternator. Now let's go to the current side. Again, A is where I turn the key on. There's my system draw. And then notice this little smear hiccup. I wonder what let's look at that closer. So I'm going to take my zoom feature right here, and I'm going to look real close right there. What do you think that is?
When you first turn the key.
I just turned to start.
That's the solenoid?
That's the solenoid closing. That's the current now passing through the contacts. Do you think if I saw that looking like a mountain range instead of a fairly smooth peak, there might be an issue with the starter? Okay, maybe that starter works today, doesn't work tomorrow. C is what we already talked about. That's that peak amperage that you're going to see. Not unusual to see 500 or 600 amps, but you'll notice that it's for a nanosecond. There's no time involved with that. The cylinder's the engine's starting to move. That's the first few cylinders. What I want to look at, though, is how long did it take from the time I turned to start until the motor was running on its own. Generally, about a second or so is good. And again, you're all trained, experienced technicians. You know if a car's dragging. You know if it's spinning over too fast. But how do you share that with your customer when they're at the office? What if you had a graphical representation that you could say, Mr. Customer, look, I don't know if you noticed or not, but it's taking way too long for your starter to work, and this is why. And here's a picture showing you, compared to a known good one. And the neat thing about modern era is that you can, if you're online and your shop's computerized, you can ship it right to their email or right to their phone. Okay, we got the car running. Notice now how we've got current going in the positive direction. Okay, this is the draw. This is going back in the battery. Remember how that little short slope on the voltage screen went up to charging voltage? Well, that's the current that brought it there. Do you think if I measured that peak level, I would have a good idea of alternator output? Sure. And again, I'm not doing anything to the alternator to hurt it to find out. And then you can see that slowly over time it starts to build. Didn't take much to restore this one back to normal. But I'm going to watch this. Now this is another benefit to this. Once you've got this basic information, let it run for a couple of minutes and watch what happens here at the end of the amperage. This is the net, right? This is what's left over after I put it back in. I've taken what I'm going to take out. If you see anything more than 3 amps net, then you've got a sulfated battery. You know, those are the batteries that test good today and test worth of crap the next day. These are the batteries that cause alternators to fail repeatedly. If you see a 10, 12 amp net, that poor alternators are going to overheat. Okay? And now again, you have a graphical representation. In fact, with the picoscope, you can actually print out a report, you know, for the customer, but you don't need all that. Just save the screen, send it to your printer, and print it out. Again, I'm going to look at the forest. I'm looking at this forest. Does that forest look different than the first one? Pretty markedly so too, right? Especially in the current. Look at all that. That's awful smeary. Now, I told you about noise before. I don't see occasional spikes up and down, right? This is a total smear. But again, I can zoom in on that smear. There's that short little section I'm going to look at. What do you think I'm looking at here?
AC ripple.
Yep. That's the AC component. Isn't that what an alternator puts out? Unless it's rectified. And what I'm truly getting are the clipped tops of the positive side of that AC voltage. Now, how do I know this is good or bad? Well, I have a known good one. A known good one's only going to show me about, this was 81 millivolts top to bottom. Not much. And I don't know if you can see it real good in your handouts, but there are definite curved humps. If you take an AC signal and you stagger them 120 degrees, just the way they come out of the alternator, that's what you see, these staggered little peaks. Okay, everybody with me? Compared to that one. See how the amplitude is much greater. In fact, it's over a volt. Got weird drivability problems going on? Check your AC voltage. If you get anything more than what Pierre was sharing on some of these newer cars, even as much as with 200 millivolts,
200, yeah.
is too much. Computers like yes, no, ones and zeros. When you start saying an AC component, aren't I giving a whole bunch of yes, no, yes, no, yes, no, yes, no, yes, no, yes, no? And the computer's going like, what the hell are you talking about? And doesn't know how to react to that. Easiest way to find out, unplug the alternator, see if the problem goes away. Okay? The other thing, I don't know if you can see in your pattern, remember I showed you on the good pattern, there were nice, round, even humps. When you see a bad one, I still see those nice round even humps, but they're embedded in the bigger peaks. Do you see that? So it's almost as if I had, or like a relative compression exam. I've got 4 or 5 good ones, and then whoop, nobody home. So in this case, one diode is not doing its share of the work. Do I care if it's shorted or open? I don't. It's bad. That's all I need to know. I didn't build it, I didn't break it, I didn't make it, but I can fix it. Here's some other uses. What about intermittent short finding? You know, the customer that comes back, you change the fuse, he goes back a month later and the fuse is blown again. What if I took a low amp clamp and I hooked to that affected circuit while I was doing my wiggle test? Yeah, I got the headlight and the buzzer, but look how quick this is hitting short. This is a 30 amp circuit. It's actually pulling a 53 amp current draw, and the fuse is not blowing because it's not happening long enough. How does a fuse work? It's a thermal device, right? It has to heat up. So you turn that back to your customer. Maybe your buzzer didn't pick it up, your bulb didn't pick it up, but your scope will. And I can set the trigger to go off when I hit that peak. When I hit any kind of current flow. This is another example of where I applied a scope to a problem. Customer coming back complaining that he was losing a battery. He wouldn't start. He had a battery drain. But the battery's in the trunk. So I'm going to try any kind of conventional parasitic drain test. As soon as I open the trunk, everybody's woke up. The lights are on. So I have a couple of choices. I can get in the trunk and have somebody shut me in and wait for everything to go to sleep and start measuring. Or I can use my scope, and that's what I did here. And I must admit, I got really lucky with this. I came walking by, and I saw this going on. And this is incorrect orientation. That's the current draw, and it shuts back off again. And at the same time I saw this, the radio was playing in the car, and the key was in my pocket. What's the radio on a Benz? It's a computer. It's a radio on a Dodge. It's a computer. Okay? But just that simple track there, that on, off, on its own, would that lead you to a module issue of some kind? Would that at least help you narrow down your direction? I think you'll enjoy this one. This young lady bought the Drawit Stratus from our dealer, and she was an employee of the dealer. The car only had 30,000 miles on it, didn't have any history on it, and it had a code set for secondary airflow insufficient. Okay, so first thing I'm going to do is I'm going to do some digging on the system. How does this work? Well, it's only on the California models. And the way it works is that the ECM turns the pump on when the engine's cold to throw air into the catalyst to get it lit off a little sooner. It only runs for about 30 seconds. The ECM provides 12 volts to a dedicated relay that then powers up the blower, pump, and there's a dedicated MAF sensor in the circuit to send the reference back to the computer. The plumbing runs from the motor through a line and up to the exhaust, a check valve that's mounted to the exhaust manifold. From there, there's a passage cast into the cylinder head that distributes the air to individual ports going to the exhaust. Okay? So now I know how the system operates. How am I going to diagnose this problem? Right now, there are all kinds of possibilities, aren't there? Relay could be bad, the pump could be bad, the MAF could be bad, could be a restriction in the system. ECM could be bad, wiring, who knows? And I can do it a couple of different ways. I could take out a bidirectional tool and I can start turning the relays on, see if it works, but it's not going to really tell me it works when it's supposed to. Not necessarily. But my scope can be set up to tell me that. And that's what I chose to do in this case. I want to see it when it's happening and when it's supposed to happen. So I got the car cold. Green is pump current, blue is power to the relay, and the red trace is the signal going back to the computer from the MAF sensor.
Let's change to that.
Is the pump running?
Yes.
Instructor.
How about the power to the relay? That's going, right? Just a real quick side note, when I do things like this, I like the back probe. Once in a while, I gotta go ahead and pierce. But if you do choose that method, make sure that you repair where you pierced. Okay, especially in areas where you get a lot of corrosion. So the blue trace is telling me that the ECM is indeed powering the relay. So all the conditions that it wants to see have been met, and it's doing its job. So do I need to worry about any of that?
No.
The pump motor is showing current flow, so the relay works, the circuit's intact, the blower motor is operational. Do I need to worry about any of that? Okay, and remember, I'm looking at a system that only runs for about 30 seconds. I got this information in about 15. What did the MAF sensor look like? Didn't change. So I either have what? A problem with flow, or I got a problem with the MAF. So what would you do next? How about we just uncork the pipe and look at it again? So the easiest place to get it is right before the check valve. So I just unplugged it, just pulled the hose off. Ran it again. Now look at the MAF sensor. Good flow. Anything wrong with the MAF sensor?
Nope.
I'm all done with that. I know I've got a restriction. And where I'm unplugged, there's only the check valve, the exhaust manifold, and the individual ports going into the head. This car's got 35,000 miles on it. Are they clogged? I wouldn't think so. But that low mileage, I wouldn't think so. So I'm thinking, what about this? Let's look at the check valve. And I don't know, this is a California car. Right? They don't make these in the other 49 states. I see this in the valve and going, that looks like crap. Let's put a valve on it. This is with a new valve installed. Made an improvement, it was better. But would you call this fixed? No, because we had wide open flow earlier, right? It went off the scale. So now it's time to pull the manifold. That's all that's left. This is what the California emissions look like. That's that channel I told you about. And these are the ports that lead to the individual, exhaust tracks. So that's what I was looking to see when I pulled the exhaust manifold off. I figured those have got to be clogged up. I'll clean them out and we'll be done. Instead, I found this.
They're blocked, right?
No hose.
There are no holes.
The wrong one.
This is a federal head. You ever run into stuff like that in the real world? I got all kinds of examples. See, the company that I work for, we have a policy that if we don't sell you a car, we'll still buy yours. And we have had guys bring us stuff that they spent money trying to fix, got it band-aided enough long enough to hide the problem, brought it to us, and we bought it. Okay, and this is an example of one. What really disturbed me, though, is when I got into it, I also saw this. This guy knew he'd done something wrong, and he actually took 2 exhaust gaskets and cut the slots to make up ports of his own.
Is this example on your website?
On the website,
I read this.
yeah, this has been on our, we blogged on this one. Why go through all that effort? I don't want to do that again. Okay. Then we have time for one more. This is a flickering PT Cruiser. Not unusual. You expect there's a problem with the charging system. You see the lights, everything flickering as it runs. So I've got the scope attached to the B+ terminal at the alternator. and one at the battery. And this is the first thing that screwed me up on this car. They actually used 3 different control methods for the field on the PT Cruiser. The schematic told me that it was ground controlled when it turned out to be power controlled. In other words, the ECM sent power to the field rather than grounding the field. But when I plugged my scope in and I got voltage, that kind of clued me in that the schematic and my service information was incorrect. That ever happen?
A little bit.
Once in a while.
Several times a week.
Now again, I have a lot of time. This is almost 2 minutes on the screen. I'm going to zoom it in a little bit. And this scope allows me to manipulate each individual pattern. In other words, I can grab it and I can move it on the screen to lay it on top of another one, or I can eliminate the ones I don't want to look at and have just one showing, or any other thing I want to do with it. So that's what I did. I laid the 2 voltage signals on top of each other, and they look like they're matching pretty good. Now, when we did our voltage drop testing, we taught guys, if you're new to it, always reference your meter to battery ground. If you're testing on the positive side of the circuit, that means you have to do the math. You have to measure the battery and then measure the power getting to the component. That difference is the drop, right? If you become proficient, then you just move the 1 lead over to the positive side, and now your meter's doing the math for you. Everybody with me on that? Well, when you're doing a charging system voltage drop test, which the tech did and did correctly, when you've got changing voltage, how are you going to do any kind of subtraction? You're not getting the 2 numbers close enough to each other to be accurate, are you? But I am with my scope. Notice the difference in drop here. Nearly a volt variance between the battery positive and what the ECM power coming out is. Is a 1 volt voltage drop too much? And if I look at where my leads are, one's on the battery, one's right at the ECM for the field, it's got to be between the 2 points, right? So it's between the ECM, the power going to the ECM, the fuse box, the cable, back to the battery. And how am I going to find it from there? You start moving back towards the battery until it returns to normal. And that's how we isolated something very simple. It turned out all it was the section of positive battery cable going from the battery to the fuse box. That cured the flickering light problem. We got a little bit more time. I got quite a few questions during the break about what's the best scope. Any scope is better than none. Look at what you need. Look at what your comfort level is. If you want something that's going to tell you or have stored known good patterns or help you to determine where to connect it, then there are several handheld models available that do that. But you're going to pay for that. And you're going to pay the updates for that to keep it that way. Barney's tools, very user-friendly. Personally, I've never needed 8 channels. But there's a lot of things that scope will do for you, like the in-cylinder pressure testing. It'll do the diagnostics for you. It'll tell you where the problem is. The Pico, I think, is probably one of the more affordable on the market, but it doesn't have all the bells and whistles. But if you can read a schematic and you know how to hook up a multimeter, it's a very powerful scope. I can record literally hours of data and do it in a manner that allows me to zoom in on minute sections of it with accuracy. Or that little UEI scope you had sitting on the back counter. I mean, back in its day, that was 5 million samples a second. That was fast. And it did me well for a long time. But like I said at the beginning, the only limit the scope has is in the imagination of its users. And with that, gentlemen, I'm going to say goodnight. Thank you. If you came here with something more, or leave here with something more than you came here with, it was a good night. I know I'm going to leave here with something more than I came with. Thank you for your time. Don't forget,